Good morning, everyone. This is a concept that we haven't seen before in this playlist, and that involves what the reading of an accelerating scale would be. The question is that any different from the regular scale reading of mg? Well, let's jump into the problem and find out. It tells us that we are standing on a bathroom scale in an elevator in a tall building. Our mass is 64 kilograms. The elevator starts from rest and it travels upward with a speed that varies with time according to the following equation here. When t is equal to 4.0 seconds, we're asked, what is the reading of the bathroom scale? Now, this is a Newton's laws problem, so we expect to use F equals ma somehow, but the question is, how are we supposed to do that if we have v here? Because it's F equals ma, not F equals mv. If we want to go from velocity to acceleration, which we can indicate here using this dotted red vector, we need to take a derivative with respect to time of this equation for the velocity. Let's go through that process next. We can begin at the top here with the symbolic representation of what I was just saying, so we can state our intention to the reader. And next, I'll plug in the expression for the velocity for vt here. And that's what this looks like. You can do the derivative in one single leap, or if you're not fully comfortable doing it that way, you are allowed to distribute the derivative operation into both of these chunks here, like this. And now, in this line, I have factored out the constants, 3.0 meter per second squared and the 0.20 meter per second cubed, in front of their respective derivatives. And so now we can see clearly what it is that we're taking a derivative of. And just as a quick reminder, here is the power rule that we are applying in this situation. And that's what I'm going to do in this next line. So the first derivative for t in the first chunk reduces the exponent to 0, and t to the power 0, or anything raised to the power 0, really, is equal to 1, so the variable disappears. And the 2 in the exponent for the second derivative comes down in front as the coefficient, and we multiply it by the constant. And notice that the t is down to an exponent of 1 here. We can simplify this expression. We don't really want to leave it as 2 times this. So let's bring that all together. And while this is useful, this represents the acceleration at any possible time. We only need it at a single time. T is equal to 4.0 seconds. So let's take this expression and plug in that time next, up above, right here. So, obviously, the multiplication of 0.40 and 4.0 is rather straightforward. But do notice that we are taking a second unit in the numerator and multiplying it by 3 units of seconds in the denominator. So it will cancel one of the units off in the denominator, so we'll end up with meter per second squared as the final units in the second chunk here. And both of these have the same units now, so we can add them together, and here's what we get. Now we can plug this into F equals ma and solve what the problem asked for. And the first step is setting up the free body diagram. It's actually going to be super simple. The only forces that we have to account for are the weight of us standing on the scale and the normal force pushing back. The normal force is actually the reading of the scale, by the way. Hint, hint. We'll come back to that in a minute. We can also plug in our acceleration off to the side, since we know that value and direction from the previous analysis. And that is it for the free body diagram at this specific time. Let's move this off to the side, and we'll get F equals ma into the picture, like we've done in many of the other problems before. We start from the top, as always, and I just choose to work in the x direction first as a preference. And this one is easy because we're just standing on a scale and we're not moving sideways. There's nothing happening. So start with the easy thing first and get it out of the way. Let's move on to the other side. In the other direction, we have the normal force pointing in the plus y direction and the weight pointing opposite to that. So that's why we have normal force minus weight, and that's equal to the mass times the acceleration in the y direction at the t is equal to 4 seconds that we solved for. And I can plug that into our next line here so we don't forget about that. And remember, when I was setting up the free body diagram, I said that the normal force is the scale reading. That's what we want. So let's solve for that. We can move the weight to the other side of the expression, like this. And next, to get a clearer picture of what's happening, I would recommend rewriting the weight as mg. So notice we have a mass in both pieces here that we can factor out, which I'll do next in this line here. So notice as the elevator accelerates upward, the scale is reading our mass multiplied by the sum of these two accelerations, g, as well as the acceleration of us speeding up as it's moving. So if we plug everything in, here's what that looks like. And I end up with the following number on my calculator here. Pay close attention to the significant figures of the values that we were given. We ended up getting 4.6 meter per second squared by working from the significant figures in the velocity equation, and those all had 2 of them. Our mass here only has 2 of them. So we need to truncate our answer to the same amount here, 2 significant figures. And so the cutoff line is after the 92. 1 is less than 5, so we have to cut this down to 920 newtons. And that is the answer to our problem. Thanks for watching.